my beautiful PU2 students, welcome back to the first chemistry session from your KCET Masterstroke, and we are going to discuss about the solution chapter. So that's gonna be one shot video in this particular chapter, along with a little bit question answer practice and full concept discussion for your PU2 as well as for your KCET. So yes, tighten up your seatbelt and stay tuned until the end of the video, and make sure that you are making a proper note during the session. So without further delay, let's get started. So here you can see this is a marking scheme or the number of questions that came throughout the year that I kept here. So this is for the KCET. You can see the number of questions that came from this chapter during this year for the KCET. It's so high. You can tell that it's one of the heavy weighted chapter in KCET. And this is for the board examination. Both of them I kept, and you can see from which zone of this particular chapter the maximum number of question came. So you can see from the colligative property, this has always been the target zone for the board people. Okay, so let's proceed. Before proceeding towards the main course, just let me tell you, if you are really preparing hard for your KCET examination and you really want to get under top 1000 rank in Karnataka, please enroll yourself in the ABHYAS KCET test series that is launched by Deeksha Karnataka, and it's going to help you to boost up your knowledge along with the practice, because it's going to provide you 35 mock tests, chapter wise previous year questions that will help to boost up your knowledge in your KCET preparation. So without further delay, enroll yourself now. So yes, in this particular chapter of the solution, we are going to cover first types of solution, concentration term, solubility, vapor pressure, ideal and non-ideal solution, colligative property, and abnormal mass. Okay, I will discuss every concept thoroughly so that you can understand from the board level up to KCET level. Okay, and a little bit of previous year question from the board as well as from the KCET I have kept here so that you can understand what is the target zone for the both KCET and the board. Okay, so without further delay, let's get started. So here we are going to start with the solution and its types. So we can see that it's three types. It can be solid solution, liquid solution, and gaseous solution. So whenever it comes to the different types of solution, please focus on the examples, common examples of different type of solution. So whenever I'm taking the name of gaseous solution, please understand that solvent phase or the physical appearance of that particular solution must be gas. Okay, so gas, liquid gas, solid gas. Remember, solvent must be gas. Okay, so now one by one example, you can see gas whenever you are discussing, it is a mixture of oxygen and nitrogen gas you can take. Liquid gas, you can take the example of chloroform with nitrogen, and whenever it comes to the matter of solid and gas, you can take the example of camphor and the like atmospheric gas or something like. Next we can come up with the liquid solution. Then remember, the physical appearance must be liquid and solvent must be liquid for that. Okay, so similarly same combination we can proceed with gas liquid, liquid and solid liquid. So gas liquid is definitely dissolved oxygen. Okay, dissolved oxygen by which the aquatic animals they survive. Okay, so oxygen dissolved in water. Next, liquid is something ethanol and water mixture that you can talk about. Solid liquid, that is any kind of solid solute. You can take the example of sugar dissolved in water. That's it. Next, you can see solid solution. Whenever it comes to the matter of solid solution, then the appearance, the physical appearance should be solid, and hence the solvent should be solid. Okay, so gas solid, liquid solid, and solid solid. So gas solid, if you just take the example, so here we can take palladium surface. They can absorb hydrogen gas on its surface, right? So that can be an example of the gas and solid solution. Okay, next we can proceed with liquid and solid. So that is an example of amalgam, means let's say mercury. In in general temperature, in normal temperature, mercury is liquid, right? So let's say mercury is making some amalgam with sodium, right? So it's a combination of liquid and solid, because mercury in general it is liquid, and solid sodium we are taking. Next you can see solid. So that is we can take the example of, you know, brush, or you can say copper and gold mixture. So this type of things you can just example you have to remember. Let's proceed further. Whenever it comes to the concentration term, one by one we will proceed with the mass percentage, volume by percentage, mass by volume percentage, parts per million, mole fraction, molarity and molality. So these are the things that we are going to cover in the concentration term. First we will proceed with the mass percentage. I want you people to note down the formula so that while doing the numerical problem you don't get any kind of issues, and please be careful about the units, okay? So mass percentage of the component, in the both numerator and the denominator, the unit will be mass, okay, weight by weight into 100. So as you can see, mass of the component in the solution divided by the total mass of the solution into 100. Okay, so whenever I'm just talking about, let's say I'm having 10% glucose weight by weight. Okay, what does it mean? It means that 10 gram of glucose is present in 100 gram of solution. So what is the amount of water here? The amount of water is 100 minus 10, that is 90 gram. So 10 gram glucose plus 90 gram water will give you 100 gram of solution. That's it. I guess it's clear to you. Let's proceed. So here we comes up with a volume percentage. So here also both the numerator and the denominator part we are going to use the volume as a unit. Okay, so you can see volume of the component in the solution divided by total volume of the solution into 100. That's it. Okay, so now again, if I just tell you that 10% ethanol solution, 10% ethanol in water, what does it mean? It means that I am having let's say 10 ml ethanol and 90 ml water. Overall the solution volume is 100 ml. Okay, I guess it's clear. Let's proceed with the weight by volume. So this is something even in the model question paper this type of questions are triggered. So weight by volume, when this comes to the picture, then this is actually used in the pharmacy. This particular unit is used in the pharmacy, okay, for to mention the composition of some ointment or any kind of medicine. Okay, so here in the numerator we use the unit of weight, and in the denominator we use the unit of volume. So mass of the component divided by volume of the solution, okay, into 100. So next it comes to parts per million. So parts per million is used whenever the concentration is very less, means it's very diluted. Let's say the amount of oxygen present in water. Okay, it's very less, right? So those type of thing. Or let's say this particular unit sometimes is used to measure the pollution in air as well, right? The amount of dust particle present in air, this type of thing. Okay, so here how we measure it? Here, number of the parts of the component divided by total number of parts of all component into million, 10 power 6. You can also get it in the form of parts per billion. Then here without writing 10 power 6, you have to write 10 power 9, that is parts per billion. Okay, in general you can just proceed with the parts per million, but in case for your KCET examination, parts per billion, just for an information I'm telling you. So here you can see a liter of seawater that contains actually 6 into 10 power minus 3 gram of dissolved oxygen, very less, right? Very diluted, right? So such a small concentration is also expressed as 5.8 gram per 10 power 6 gram of seawater. Okay, means 10 power 6 means million gram of seawater. I am having only 5.8 gram. Right? I guess it's clear to you. Let's proceed further. This is the mole fraction concept. So what is mole fraction? This is basically the number of moles of the component divided by the total number of moles. Okay, so here you can see next this is how actually we represent. Okay, if you are having the binary mixture, okay, binary mixture in the sense, let's say I am having only two components present in my solution, A and B. Let's say number of moles of A, B, N of A, number of moles of B, let it be N of B. So from here, sorry, this should be X of A. From there, if I want to find out the mole fraction of A, then for that case, number of moles of A divided by total number of moles. Okay, so it's not necessary always it will be a binary mixture. It can be multiple components can be there. Let's say A, B, C, D, like up to the ith component present over here. Let's say I'm having A, B, C, D up to ith component. Okay, so what is the mole fraction of I? Okay, what is the mole fraction of ith component, right? So how you should represent? Here also number of moles of I divided by total number of moles. So Na plus Nb plus Nc, okay, up to Ni. Okay, summation of all the species. Okay, and always remember mole fraction for the binary case, mole fraction of two species is always going to be 1, right? And another case, if it is not a binary species, it is binary mixture, if it is a mixture of the multiple species, for that case also, if I just add XA plus XB plus XC, okay, up to XI, okay, that also going to give you 1. Summation of the mole fraction of all the components present in a solution always will give you 1. I guess it's clear to you. Let's proceed further. Here you can see one problem comes. Let's target it. Okay, answer is also given. Let's just give it a try. Okay, calculate the mole fraction of ethylene glycol in a solution containing 20% of ethylene glycol by mass. Okay, let's do it. So here they are saying 20% by mass, right? 20% of ethylene glycol. Right? What does it mean? So whenever they are saying that ethylene glycol is 20%, it definitely means 20 gram of C2H6O2 ethylene glycol and 80 gram of water, right? This is only the weight by weight, percentage weight by weight, right? So from here, see, amount given weight I got. From here number of moles we can calculate. Okay, so number of moles of, let's calculate number of moles of ethylene glycol. I'm just writing ETG. Okay, number of moles of ethylene glycol I can calculate, that is 20 divided by molecular weight of ethylene glycol is 62.08. Okay, so now if you calculate this, you will get almost something like 0.322 mole. Okay, now if you calculate for water as well, it will give you 80 divided by 18. So that will also give you something like how much? 4.4 mole, right? So now what you have to find out? You have to find out the ethylene glycol, right? So this is your step 1, this is your step 2. Here I am doing the step 3. So, okay, let me just mention them. This is your step 1, okay, this is your step 2, and this is my step 3. Here I have to find out the mole fraction of ethylene glycol. So that's going to be number of moles of ethylene glycol, divided by total number of moles. So number of moles of ethylene glycol plus number of moles of water. So let's put the value over here. If you put it 0.322 divided by 0.322 plus 4.4, that will give you 0.0677 something. Okay, so that's going to be your answer. Okay, I guess this thing is clear to you. So this is how you need to trigger this type of problem. I guess it's clear. Let's proceed further. So here you can see we are coming across towards molarity, molality, and let's proceed one by one. Molarity, so the formula is number of moles of solute divided by volume of solution in ml. Okay, volume of solution. Okay, denominator part, sometimes they ask in your MCQ for the board examination. Please be careful. For the molarity, in the denominator we are going to write the volume of solution. Okay, now the moles of the solute, moles can be written as given weight by the molecular weight. Okay, so and the rest of the things are similar. Okay, now you can see if you are having 0.25 molar solution. Okay, 0.25 molar, here they gave NaOH, right? What does it mean? It means that you are having 0.25 mole of NaOH in 1 liter water. Okay, this is what the molarity indicates. I guess it's clear. Let's proceed. Okay, let's trigger one problem. Calculate the molarity of a solution containing 5 gram of NaOH in 450 ml of solution. Okay, so we can directly put it into the formula. So I am having, let's say, molarity, that is equals to W2, that is the given weight of solute, M2, that is the molecular weight of solute. Here I am going to multiply volume of solution, that I am going to take it in ml into 1000. Let's put it. So here basically I am having 5 gram, right, into 1000 divided by molecular weight of NaOH is something like 40 gram per mole, right, into volume is something like 450, right. So from here if you calculate the entire thing, it will come up to be 0.278 molar. Okay, so that's going to be your answer. I guess it's clear to you. Just simply I just put the formula and just put the values and just calculation, that's it. Okay, so yes, let's proceed further. Here you can see this is molality. So the main difference is there in the denominator part. So molality is basically the moles of solute that is present in the mass of solvent. In a like 1 kg of solvent, how many moles of solute is present, that is your molality. So in the denominator part you have to take the mass of solvent. Okay, mass of solvent. So in the similar way, moles you can just split it in the W2 divided by M2 into 1000 divided by the mass of solvent. That's it. Okay, so now if I just tell I'm having 1 molar solution, 1 molar solution, what does it mean? 1 molar solution means 1 mole of that particular solute is present in 1 kg of water. So here they have given the example of KCl. So KCl molecular weight is 74.5, means I am having 74.5 gram of KCl. 1 mole means molecular weight, right? So I am having 74.5 gram of KCl present in 1 kg of water. This is how the molality can be defined. I guess it's clear. Let's proceed with a problem. So here you can see, calculate the molality of 2.5 gram of ethanoic acid and 75 gram of benzene. So again we are just going to put the formulas over here and we are just simply calculate it, that's it. Okay, so molality if you write, okay, so that's going to be W2 into 1000 divided by M2 into mass of the solvent, right? Mass of solvent, that I am taking in gram because I already multiplied there with 1000. Okay, so from here let's put the values. 2.5 they have given. Okay, molecular weight of ethanoic acid is 60 gram. Okay, here it is gram, here it is 60 gram per mole. into mass of the solvent. How much? 75 gram benzene they have given. 75 gram. So now if you just simply calculate this, your answer will come something like 0.556 molar. Okay. So this type of simple calculation you can get out of it. Okay. Let's proceed. So here we are going to discuss about the solubility. So we have done with the concentration part. I guess you have understood. So any problem if you feel that it seems difficult from the concentration zone, means concentration term, please make sure you are just mentioning them in the comment section. So definitely I will be answering them over there. Okay. Okay. So let's proceed with the solubility. So here you can see what is solubility. At first we are going to discuss, then solubility of solid in liquid we are going to discuss, then solubility of gas in liquid. So what is solubility? Solubility of a substance is basically the maximum amount of that particular substance can be dissolved in a specific amount of solvent. Okay, that is called solubility. The maximum amount of that substance can be dissolved in a solvent. Okay, specified amount. Okay, so here definitely the solubility differs in pressure, temperature. So definitely whenever you are just trying to find out the solubility of a particular substance, please keep your temperature and pressure fixed. Okay, so now we will proceed with the solubility of solid in liquid and the solubility of gas in liquid. Okay, so first let's see solubility of solids in liquid. Here it depends upon the nature of the solute and solvent, and then dissolution and crystallization, then types of solution, then effect of temperature we will proceed, then effect of pressure also. So one by one let's proceed. First is nature of the solute and solvent. It's going to be very important. So it's not something like any solid you put in any liquid and they will get dissolved. Okay, just let's take one example. If you take oil and if you put it in water, will it be miscible? No, right? So what's the reason behind it? There lies a very beautiful concept that is called like dissolves like. Means if any solute wants to get soluble in a particular solvent, they should be of similar size, similar nature. Okay, like if you just going to add sodium chloride or sugar, they can be easily dissolved in water. Why? Because water is polar and your NaCl compound is also polar, right? So polar solvent likes polar solute, right? But those particular in water only, if you want to put anthracene, naphthalene, they will not get soluble because these particular things are organic and they are non-polar. They need non-polar solvent to be dissolved, right? So I can take the example of benzene, that is a non-polar one, and if you want to put some naphthalene in benzene, they can be soluble nicely. Okay, so this is called like dissolves like concept, right? So I guess you understood that polar solute, they likes polar solvent, and non-polar solute like non-polar solvent, like this. I guess it's clear to you. Let's proceed further. Here comes dissolution and crystallization. So when a solid solute is added to a solvent, it gets dissolved, right? So this particular process is called dissolution. Now what is crystallization? So crystallization is basically like any sum of the dissolved solute particles, if it returns to the solid phase, okay, once it is dissolved, okay, so that solute particle, if it returns to the solid phase, it is called crystallization. Okay, so now you can see both when both the process occurs at the same rate, okay, that's called dynamic equilibrium. Okay, means solute plus solvent, they will give you the solution. So what is the moral of the story? First you put some solute in the solvent. What will happen? It will get dissolved. The process is called dissolution. Then what will happen? That dissolved solute can come back to its solid phase. That is called crystallization. When these two processes occurs in same rate, a dynamic equilibrium is established. Okay, I guess it's clear to you. Let's proceed. Now here we are going to discuss some types of solution. First is saturated and unsaturated. So saturated solution means like no more, you can't add more solute to that. Okay, no more solute can be dissolved at a given temperature and pressure to that particular solvent. Okay, this is called saturated solution. Unsaturated solution means more solute you can add that can be dissolved under the same condition. Okay, I guess it's clear. Next you can see we are going to discuss one by one effect of temperature and effect of pressure. So definitely here Le Chatelier principle is going to work. Okay, so whenever it comes to the matter of the temperature, first, if the dissolution process is endothermic, dissolution means, I guess you remember, you are adding that particular solute in that solution and that particular process is endothermic, means it takes up heat, right? Then if you give temperature, your solubility will increase. If you give temperature, solubility will increase because solubility is inversely proportional to temperature. That we will see, okay, later on how it's coming from the Henry's law. Always remember, if the dissolution process is endothermic, if you give temperature, then your solubility will increase with time. Okay. Next, if the dissolution process is exothermic, means it releases heat, then solubility decreases if you give temperature. Okay, backward reaction will be triggering out if you give temperature, right? So that's the reason you can tell that solubility will decrease. Okay, now let's proceed with the effect of pressure. So now whenever it comes to the solid and liquid solution, then there is very negligible effect of the pressure on the solubility, but whenever it comes to the gas and liquid, pressure has a crucial role in it. Okay, so here you can see the reason of that particular case, why solid and liquid solution pressure has very negligible effect. Why? Because it is means solids and liquids are incompressible, right? If you even apply pressure, they will not be compressed that much. But if you just take it a gas, then definitely the gas particles, they are having space in between them, they are compressible, right? So they have very crucial effect of pressure when you are making the solution. I guess it's clear to you. Let's proceed. So here we are going to target solubility of gas and liquid. First a little bit introduction, then we will proceed with the effect of pressure. From there Henry's law will come, effect of temperature, and we will just find out some key points out there. Next you can see first is little bit introduction, that is many gas, they can be dissolved in water. Just one example, like oxygen, they are very slightly soluble though. Those dissolved oxygen, okay, that are present in the water, that gets the support to the aquatic animals, right? And highly soluble in water, that is HCl. Okay, now key factor that affects the solubility, first is pressure and next is temperature. Let's proceed. So here comes the effect of pressure. So dynamic equilibrium definitely exists. So gaseous molecules, they enter and leave from the solution in the equal level. So if you just see any gas you want to dissolve in the particular solvent, then it will come and it will go. Okay, it will come, it will go. It's not something like it will go and it will be there only. No. So there exists an equilibrium out there. Okay. Now, if you keep increasing pressure, compressibility of gas is very high. So gas will be compressed out there. So more particle will strike the surface area of the solvent. Okay. As a result of this, solubility of the gas will increase. Okay. Now, a new equilibrium will be established that will take you to a higher solubility. I guess it's clear. So what is the moral of the story? In general, there exists a dynamic equilibrium. Gas particle comes and go, comes and go, comes and strike the surface and go. Right? Now if you increase the pressure, so gas particle will be compressed, they will be forced to strike on the surface, right? So once they will strike on the surface, solubility will increase and the new equilibrium will be established. I guess it's clear. Let's proceed. Okay, so here we are going to discuss about the Henry's law, that is related to the definitely pressure dependency or of the solubility. So basically what it is saying, statement of the Henry's law is very important for the PU board examination, okay, and the mathematical form is also important for the numerical purpose for the board and KCET as well. Okay, so Henry's law is definitely it's going to be a gas law that states that at that amount of gas that is dissolved in a liquid is directly proportional to the partial pressure of that gas above that liquid. Means more the pressure, solubility will increase, directly proportional to the partial pressure. Okay, so that's the reason partial pressure of the gas is directly proportional to the mole fraction of the gas. Here mole fraction of the gas indicates the solubility of the gas. Okay, means how much gas is soluble. You can take the term this many number of moles of gas get soluble. Okay, so number of moles is associated to mole fraction, so I can actually designate the solubility with respect to mole fraction, like that. Okay, now if you just remove the proportionality sign, there will come a constant, that is KH, that is called Henry's constant. Okay, I guess it's clear to you. So for the board people, let me just tell you, my dear, whenever you are writing the Henry's law, if they are asking like state Henry's law, please make sure that you are writing the mathematical equation as well, along with the abbreviation of each and every terms. I guess it's clear to you. Let's proceed. Okay, so here comes interpretation. You can see, so each gas, they have a different KH value. It depends upon the nature of the gas, and always remember, higher the KH value, lower the solubility. Why? Because from this particular equation you can see KH is basically inversely proportional to mole fraction of gas, right? So if KH is increased, solubility will decrease. They are inversely proportional. I guess it's clear to you. Yes, let's proceed. So here comes the application of Henry's law, very important. 3 application we will discuss. 3 of them you have to remember. They can give you the question in the board level, 2-marker question they can give. Okay, so please remember them. First is to increase the solubility of carbon dioxide in your soft drinks. Okay, so I guess you people know it very well. Whenever you are just opening the knob of this particular cold drinks, that's very much favorite to you people. I know you people take at least twice in a week, right? So yes, what happens basically, sound comes whenever you are just opening it, and it feels like some pressure is released and some gas comes out of it, right? So what basically happens, with a high pressure, CO2 gas is dissolved in that particular soft drinks. Okay, so yes, be careful, don't take that much cold drink, because that's going to harm your body, because you are going to take dissolved carbon dioxide in your body, right? So yes, that carbon dioxide gets dissolved under high pressure, because in high pressure solubility increases. Okay, next you can see scuba diving. Okay, for the scuba diving, what basically happens, let me just tell you, whenever the scuba diver, they are having the tank with them, in that oxygen, nitrogen gases are there mixed, okay, in a particular ratio. So when they go inside, when they go going down, right, what happens? Water pressure increases, right? Water pressure increases slowly. What happens then? Nitrogen gas in the tank becomes more soluble in the blood vessels, in the blood, okay, rather than that of oxygen. So that time what happens, whenever he is going down, nitrogen gas gets soluble in the blood. Now whenever, if he comes out rapidly, if he coming out from the deep to the very surface area very quickly, then what happens? The pressure releases, the water pressure releases. As a result of this, the nitrogen gas starts to bubble out from the blood. Okay, nitrogen gas that was initially it was soluble, but now the pressure is released, right? So the nitrogen gas starts to bubble out from the blood. As a result of this, it's a very painful disease, and that's called bends, right? So in order to prevent those things, nowadays that particular tank, it contains a mixture of helium, nitrogen and oxygen. So in presence of helium, nitrogen gas doesn't dissolve in the blood in high pressure. Okay, so that's the reason it is diluted with the helium gas. You can see the percentage, 11.7% of helium, something 56% I guess it's nitrogen, and the rest of the 32 I guess it's oxygen. Okay, so that is the composition inside the tank that is maintained now. In that particular composition, nitrogen gas don't gets dissolved in the blood to avoid the bend. I guess it's clear? Yes, let's proceed. One more, that is the anoxia, right? So what happens whenever you are going to a mountain? See, I'm a mountain girl. I love mountain. So yes, I felt personally that this type of problem happens whenever you are going to the higher altitude. Okay, so basically what happens? You are here whenever this is the zone, it is a sea level, right? So here the atmospheric pressure is 1 atmosphere, right? Whenever you are going up in the higher altitude, the atmospheric pressure gets reduced, right? So as a result of this, the amount of oxygen that needs to get dissolved in the blood, that also gets reduced, because what happens? Pressure decrease, so amount of oxygen gets dissolved, that is also reduced. So brain doesn't get enough oxygen supply. As a result of this, it loses its thinking ability. Sometimes you may feel nausea and all because of the less oxygen supply in the brain. Okay, your weakness, confusion, this type of things you can feel in the higher altitude, that is called anoxia. Okay, so I guess these 3 applications are clear to you. Let's proceed further. Yes, one more. In the cold water, any aquatic animal, they always prefer to be in the cold water rather than that of the hot water. Okay, so in the cold water, what happens basically? Let me just tell you. Temperature is inversely proportional to the solubility. Okay, so if you increase the temperature, then solubility will decrease. So if you decrease the temperature, solubility will increase. That's the reason whenever the water is cold means temperature is decreased, means solubility of oxygen is more, right? So aquatic animals, they get more supply of oxygen in the cold water rather than that of the hot water. So thus they prefer cold water to sustain. I guess it's clear to you? Yes, let's proceed with the problem. Okay, let's see. If nitrogen gas is bubbled through the water at 293 Kelvin, how many millimoles of nitrogen gas would dissolve in 1 liter of water? Okay, assume that nitrogen exerts a partial pressure of 0.987 bar. Given that Henry's law constant is this. Okay, fine. Let's do it. So definitely once they gave the Henry's law constant, definitely you have to follow the Henry's law here. Okay, so how you should follow? Write the formula at first. Partial pressure of gas is equals to kH into mole fraction of gas. Okay, from here what I can write? That is equals to kH. Mole fraction I can break a little. That is number of moles of what gas is this? Nitrogen divided by number of moles of nitrogen plus number of moles of H2O. Now let me tell you one thing, my dear. Whenever a gas is dissolved in water, the number of moles of that particular gas is very less compared to that of the number of moles of water. So you can simply neglect it. Okay, so what is the reason? Number of moles of water is greater than that of, very greater than that of number of moles of N2. So from here I can simplify it. H2O plus number of moles of N2, I can write it as number of moles of H2O only. Yes. Now what I have to do? Let's put the values. Okay, so how much it's given? 0.987, right? Sorry, 0.987. 0.987, okay, equals to KH value is also given 76 point, okay, this is kilobar, okay, we will convert it into bar, okay, 76.48 into 10 cube bar. Okay, number of moles of nitrogen that I have to calculate, number of moles of nitrogen I have to calculate divided by number of moles of water. Okay, they have said that it is 1 liter. Okay, so 1 liter is equivalent to 1000 gram. Okay, because the density of water is 1. So 1000 gram. So now you can just apply the formula of number of moles given mass by molecular weight, that is 18. From here you will get 55.5 mole. Let's put it here. So 55.5 mole. Fine. So now number of moles of N2 you have to calculate, right? So if you want to calculate, then overall the things will come 0.987 into 55.5 divided by, this is mole, bar will be cancelled out, divided by 76.48 into 10 cube. Okay, so if you come up with this, then your answer will be something like 0.716 into 10 power minus 3 mole. Okay, so this is your mole. From mole I have to convert it to millimole. See, they are asking in the unit of millimole. So simply that's going to be just here I can do it 0.716 into 10 power minus 3 into 10 cube. Okay, millimole if you want to convert, just multiply with 10 cube, you will get 0.716 millimole. Okay, I guess it's clear to you. So your answer is, let me write the answer here. So your answer is basically 0.716 millimoles. I guess it's clear to you. Yes. Okay, let's proceed. So now effect of temperature. Okay, so solubility decreases with the rise in temperature. Okay, so this is for the effect of temperature whenever the dissolution of gas is exothermic, heat is released. Okay, so what you have to do, if you if you just if you just make the temperature high, solubility will decrease, that is in the exothermic case. Okay, so in accordance to the last Chatelier principle, what basically happened, increasing temperature shifts the equilibrium backwards, so less gas will be dissolved. Okay, solubility will decrease. Okay, I guess you understood. So gases dissolves better definitely in cold water. Okay, let's proceed. These are the key points that you must remember. So solubility increases with pressure because they are directly proportional. Solubility decreases with temperature because they are inversely proportional. Okay, Henry's law, important, and important for the industry, medicine, and for the environmental perspective as well. Okay, I guess it's clear. Let's proceed with the vapor pressure. Okay, first we will discuss about what is vapor pressure, then vapor pressure of liquid solution, then vapor pressure of solution of solids in liquid. Okay, so what is vapor pressure? Just let me tell you at first. So basically what happens, if you just take normally a bottle, a transparent bottle, so in that case, just on the surface of the liquid, just on the surface of your water, what happens? Is that empty space? No. There actually exist the vapors of water, right? So what happens? There exists an equilibrium. Water gets evaporated, it comes to the vapor phase, again that vapor gets condensed and come back to the water, and dynamic equilibrium goes on inside that particular empty space. Okay, so here what happens, those vapors that are coming out because of the evaporation of the liquid, those vapor, they collide on the wall of the container and as well as on the lid as well. So that pressure that is coming out because of the collision of the vapors of the liquid, it's called vapor pressure. Okay, always remember this evaporation and condensation, okay, they occurs in the same rate, okay, and definitely from the surface of the liquid, okay, so not from the bulk, rather from the surface, okay. So now what happens if you increase the temperature? Increasing temperature will enhance the vapor because evaporation rate will be high and vapor will come more and vapor pressure will increase. I guess it's clear to you. Let's proceed. This is all about the vapor pressure. Okay. Here comes the Raoult's law. Raoult's law is none other than the a modified Henry's law, quite similar. Okay, but the composition here I am taking, in Henry's law we took gas and liquid, right? But here we are going to take two volatile liquids. Two volatile liquids. Here also comes the same thing. Okay, so what happens, you can see vapor pressure of each component of the solution is directly proportional to its mole fraction. So if you increase the pressure, again that if you just see vapor pressure of the component, that is basically the directly proportional to the mole fraction. They are also mole fraction of the gas we used. Okay, so let's proceed. Let's say we are having binary mixture A and B, both of them are volatile liquid. So pressure of A is directly proportional to the mole fraction of A. Now if you remove the proportionality sign, there will come a constant. Here the constant that we are using, that is also pressure of that particular liquid at its pure state. Okay. Now in Raoult's law, what we are doing? We are mixing A and B. But A has its own individual identity, right? It has its own unique vapor pressure, that is PA0. That's constant. Okay, for the PB also it's same. PB is directly proportional to mole fraction, and once you are just removing the proportionality sign, it will come up with PB0. PB0 is the vapor pressure of B at its pure state. Clear? So furthermore, we will come back to the vapor phase, vapor phase composition, YA, we will come back to it. So now from those particular case, PA and PB, what we can tell? We can apply here Dalton's law of partial pressure. What it says, if you want to calculate the overall pressure of that solute, right, of the solution. So what is happening? I am having the pressure of A and pressure of B. Okay, so I can simply add them. That is the Dalton's law. So what is this basically? The total pressure over the solution phase in the container will be the sum of the partial pressure of the components. So sum of the partial pressure I am having PA and PB. Add them, PT equals to PA plus PB, and PA is PA0 of XA plus PB0 of XB. Right? Add them. That is your Raoult's law. Okay. Now if you simply plot it, it will come up like this. Okay, so basically what happens if you just continue a little bit from here. Here I am having PA0 XA plus PB0. Here let's write 1 minus XB, 1 minus XA, right? That is PT. From here I can get PT equals to PA0 of XA plus PB0 minus PB0 of XA, right? So now from here I can take it common. So PT equals to, from here I can take XA as common, from here PA0 minus PB0, PA0 minus PB0, here I am having plus PB0, right? So here if you just look at this particular equation, it's nothing but a straight line equation, right? So vapor pressure, that is PT, with respect to mole fraction, here this is my Y, right? This is my X. PA0 minus PB0, that is my M. Right, and PB0 is the C, that is the intercept. You can see here P10 or PA0, anything. for the two equations. See here with this respect I am getting this equation, one line. Okay, another perspective XA also I can replace with 1 minus XB, I will get another equation, right? So for those cases PA0 and PB0 will be the intercept. See these two. Okay, so now you connect, if you connect the intercept you will get the total pressure. Okay, so this is how it's a straight line equation, and if you just put it here, if you want to plot the graph, it will give you a straight line like this. Okay, I guess it's clear to you. Now one more thing that I wanted to tell, that is the vapor phase composition. So basically here in the vapor, if you just look at the vapor, it's having the component of both green and red, because A and B only we added here, right? A one volatile liquid and B one volatile liquid, right? So here in the vapor we are having the composition of the both red and green like that, right? So what is the composition in the vapor of A? If I ask you, this is the formula. YA. YA is the vapor phase composition of A. How I should write it further? So YA can be written as PA. PA I can write it as PA0 of XA divided by total pressure. Total pressure I can write from the Raoult's law, PA0 of XA plus PB0 of XB, like that. Okay. So similarly for the YB, vapor phase composition of B also I can find, that is PB0 of XB divided by PB0 of XB plus PA0 of XA. So these two things. Now one more thing that I wanted to tell, vapor phase composition, that is YA plus YB. Any component, maybe I am having even more component. Okay, so always the sum will be 1. Okay, I guess it's clear to you. Yes, let's proceed. Okay, I am having a problem. Let's do it. Okay, so what they are saying, vapor pressure of chloroform and dichloromethane at 298 are 200 mm of Ag and 415 mm of Ag respectively. Calculate the vapor pressure of the solution prepared by mixing of this of CHCl3 and this of CH2Cl2. Fine. And vapor phase composition also you have to find out. It's going to be a huge problem. It's okay. Let's do it. Okay. So here at first what we are going to do, molecular weight. Let me tell you my dear, molecular weight of CHCl3 means chloroform, it's going to be 119.338 gram per mole. Okay, and for the dichloromethane, it's going to be 84.93 gram per mole. That is a molecular weight. Okay my dear, so let's find out the number of moles. So one by one let's do number of moles of CHCl3. So that's going to be how much they gave? 25.5 gram, 25.5 divided by 119.3. Okay. Here I will get 0.214 almost mole. Okay. Next, number of moles of CH2Cl2, if I calculate, how much they gave? 40 gram. So 40 divided by 84.93. 84.93. I will get something 0.471 mole. Okay. So from here, mole fraction I can calculate. Mole fraction of CHCl3. Mole fraction of CHCl3, that's going to be 0.214 divided by 0.214 plus 0.471, right? That's going to give you something 0.312. Okay, similarly we will do for mole fraction of CH2Cl2. That's going to be 0.471 divided by 0.214 plus 0.471, right? If you calculate, this will give you something 0.471. Okay, so I have calculated the mole fraction. Next, let's put them into the total pressure. Okay, so total pressure, if I want to write it, mole fraction of CHCl3 plus P, sorry, it's not plus, it's into. Mole fraction of CHCl3 into P0 of CHCl3 plus mole fraction of CH2Cl2 into P0 of CH2Cl2. Okay, let's put the value. Mole fraction from here I can take CHCl3, that is 0.312. 0.312 into how much they have given? 200. Okay, into 200 plus, here I am getting, okay, one mistake I did here. These value, if you calculate, no, this will come as 0.688, sorry, 0.688. I know you people, crazy people, once the teacher does the mistake, you people get very much happy, right? Ma'am did the mistake. Okay, fine, I rectified. My bad. Okay, so 0.688 into 415, right? So if you just calculate this, it will come up as 347.9 mm. This is 3, okay, mm of Hg. Okay, first part we are done. Okay, calculate the vapor pressure of the solution. So first part is done, that is 347.9 mm of Hg. Let's proceed with the next part. We have to find out the composition. So Y of CHCl3, that's gonna be P of CHCl3 divided by PT. Okay, PT we have calculated already, but P0, P of CHCl3 is P0 of CHCl3 into mole fraction of CHCl3 divided by total pressure. Total pressure is something 347.9. Okay, let's put the value here. So that's gonna be 0.312 into 200 divided by 347.9. If you calculate this, it will be 0.179. Okay, so vapor phase composition of chloroform is 0.179. And next, if you proceed with the CH2Cl2 dichloromethane, sorry, that's going to be pressure of CH2Cl2 again divided by total pressure, that is P of CH2Cl2 of 0 into mole fraction of CH2Cl2 divided by total pressure, that is 347.9. Let's put the value from here, 0.688. 0.688 into 415 divided by 347.9. If you calculate, it will come up with 0.821. This is the vapor phase composition of CH2Cl2. I guess it's clear to you. A little bit lengthy but easy. Okay, the direct application of the formulas. Okay, let's proceed. Okay, so here you can see vapor pressure in solid in liquid solution that we are going to proceed. It's going to be super easy because adding a non-volatile solute to a solvent lowers its vapor pressure. Okay, basically what happens, once you are adding any kind of non-volatile solute, they are not volatile, they will not form vapor, right? So in that particular case, what happens, they gets accumulated on the surface of the volatile liquid. Okay, let's say this is my volatile liquid, this is my volatile. Now I am adding here some non-volatile solute. Okay, so they gets accumulated on the surface. They block the surface area. This is my non-volatile solute. Okay, they block the surface area. As a result of this, the vapor that should come out from the volatile solvent, it's not coming out, the vapor pressure will decrease. And if you want to find out the vapor pressure of the entire solution, so from where the vapor is coming? Only from the yellow. Only from the yellow over here, that is from the volatile liquid only. That too is lowered a little bit, right? That too is lowered. Okay, so the total pressure will be accountable only because of the volatile liquid. Okay, I guess it's clear to you. Let's proceed. Here we will come up with the ideal and non-ideal solution. So ideal and non-ideal means, ideal means it obeys Raoult's law, and non-ideal means it doesn't obey Raoult's law. So again, in non-ideal there can be of two types. One is positive deviation of Raoult's law, next is negative deviation of Raoult's law. Again, in the non-ideal cases we can find a different type of thing, not a different type, rather something important, better to tell, Azeotropes. So let's proceed with the ideal and non-ideal solution. This is the difference, very important for your board examination. Okay, it obeys Raoult's law, it doesn't obey Raoult's law. For ideal cases, in enthalpy of the mixture is going to be always 0 for that case. For non-ideal case, it's not going to be equals to 0. Okay, delta V mix. Okay, after mixture the volume should be equals to 0. There is no change in volume, but in non-ideal cases there will be either greater or lesser. Okay, interaction. Let's say I am having A and B, two different cases. Individual interaction in between A and B, they should be equal whenever A and B is mixed as well in ideal case, but for non-ideal case they should not be equal. Let's proceed. This is a positive and negative deviation, very important. The interaction, positive deviation, AB interaction is weaker than that of the individual interaction. And in negative case, the interaction is stronger, AB interaction is stronger than that of the individual one. Rest of the things you can see, total pressure is greater than that of the individual pressure summation, and for this case, lesser. Delta H mix greater, delta H mix lesser. Okay, examples are also given. You can see ethanol and acetone. So let me just tell you about it. Ethanol, individual ethanol is having very nice hydrogen bonding, and acetone also it is having very nice dipole-dipole interaction, polar molecule, right? So now individual interaction, let's say ethanol interaction and acetone interaction is very nice, very stronger. Now if you are mixing ethanol and acetone, what is basically happening? In between two ethanol, where hydrogen bond was formed, acetone is coming in between, right? As a result of this, the interaction gets weaker. So AB interaction, ethanol-acetone interaction is weaker than that of the ethanol and acetone interaction. I guess it's clear to you. For this case, let me just tell you, my dear, whenever it comes to the mixture of chloroform and acetone, so basically chloroform is CaCl3 and acetone, right? So now whenever you are mixing them, chloroform, hydrogen and acetone, they can make a nice hydrogen bonding. Okay, so let me just show you one thing. And if you just write the acetone here, they can form nice hydrogen bonding. So AB interaction, chloroform acetone interaction is greater than that of the individual chloroform and acetone interaction. That is negative deviation. I guess it's clear. Let's proceed. Yes. So this is the graph. This is how it looks like. Positive deviation means you can see the curvature is towards the positive end. For this case, it is towards below. Okay. Okay, Azeotropes definition is very important. Okay, so what is Azeotropes? It is a binary mixture definitely, and having the same composition in the vapor phase and in the liquid phase as well, and they boils at a constant temperature. Okay, so as they boils mixture, they boils at the same temperature, it's not possible to separate them out using the fractional distillation. Fractional distillation, we use different boiling point, right? Using the distillation apparatus, we just keeps boiling them in a different temperature and they gets separated. But here they boils at the same temperature, how you are going to separate them, right? So that's the reason. Please remember, azeotropic mixture, they cannot be separated using the fractional distillation. Okay, I guess it's clear to you. Let's proceed. For this case, azeotropes are also of two types. One is maximum boiling azeotrope, one is minimum boiling azeotrope. So what are the difference? So maximum boiling azeotrope is shown by the solution which shows negative deviation. Negative deviation will show maximum boiling azeotrope and positive deviation will show minimum boiling azeotrope. Okay, and the example you can see, only in this composition they will show the azeotropic mixture, that is a 68% nitric acid and ethanol, 94.5% ethanol. Okay, I guess it's clear. Okay, one question. The azeotropic mixture of water and ethanol boils at this temperature. When this mixture distilled, it's possible to obtain. Okay, so azeotropic mixture. So when this mixture is distilled, distillation, fractional distillation is not possible, right? So it's going to be neither H2O nor C2H5 in their pore state. They cannot be separated, right? Let's proceed. Okay, one more question. Solution, it's a previous year question, you can see. A solution A contains acetone dissolved in chloroform. And solution B contains acetone dissolved in carbon disulfide. The type of deviation from Raoult's law shown by the solution A and B. So this example we just have done. Okay, chloroform and acetone. What type of interaction? Negative deviation. I told you the reason, because they can form hydrogen bond. And carbon disulfide, one more is acetone. They shows positive deviation, right? So option B is going to be the correct one. So let me just show you once. Here comes the example. Okay, I already told you, explained here. I guess it's clear. Let's proceed. Okay, now we are going to discuss about the colligative properties, one of the most important thing. Okay, so whoever was still diverted up to this point of the lecture, please concentrate your mind at this point, because that's gonna be super important for your both board examination and KCET as well. Maximum number of question comes from here. Okay, so colligative property. First, why we observe the colligative property? Whenever we are using a non-volatile solute in volatile solvent. What we use? Non-volatile solute in volatile solvent. What happens here? So as I told you, non-volatile solvent, they can nicely comes out in the form of gas in order to contribute in the vapor pressure. But whenever you are adding some non-volatile solute in it, whenever you are adding some non-volatile solute in it, what happens? That non-volatile solute, they gets accumulated on the surface of the volatile solvent, right? Surface of the volatile solvent. They block the surface area. From where the evaporation takes place? From the surface. Now the surface is blocked. So vapor pressure will be reduced, right? As a result of this, the properties that will be exhibited by that particular solution, they are called colligative properties. Okay, so yes, let's proceed with one by one. First is relative lowering of vapor pressure, next is elevation of boiling point, depression of freezing point, osmosis. RLVP, relative lowering of vapor pressure. I don't have to tell you, I already told that if the surface area is blocked by the non-volatile solute, then what happened? The vapor pressure will decrease. That is a relative lowering of vapor pressure, right? So this relative lowering of vapor pressure, this entire thing is called RLVP. Del P means change in vapor pressure divided by P. Okay, that is equals to the mole fraction of the solute itself. Okay, RLVP is directly equals to the mole fraction of the solute. Okay, for now if you just break it down, that is NB divided by Na plus NB, right? Just mole fraction term I broke down. Now if you want to find out for a very dilute solution, what will happen? Let's say Na Na is very, very greater than that of the Nb, then what will happen? Then I can neglect Nb, so I can just take Na in the denominator part, right? I guess it's clear. Yeah, let's proceed. Okay, one problem. Let's target. Okay, the vapor pressure of water in the solution having 50 gram of urea dissolved in 850 gram of water. Let's find out. Okay, so let's find out the number of moles at first. Number of moles of urea. Okay, so that's going to be how much? 50 gram of urea they gave. 50 gram divided by molecular weight of urea is 60 gram per mole. Okay, 5 by 6, right? 0.833, I guess. Okay, now number of moles of water. It's going to be how much? 850 gram. 850 gram divided by 18 gram per mole. Okay, if you calculate 47.22, I guess. Okay, now let's put the mole fraction of water. That is basically number of moles of water. So here also I can write number of moles of water plus urea. That is, I'm writing N total, means number of moles of water plus number of moles of urea total. Okay, so it will come up to be, if you put the value 47.22 divided by 47.22 plus 0.833. Okay, if you just calculate this, it will come up as 0.9827. Okay, so now let's calculate the pressure. So pressure of solution. So that is nothing but P0 of water from the Raoult's law, right? P0 of water into mole fraction of water. Okay, so here you can see urea I am adding, right? Urea is a non-volatile solute. It is not having, it will not contribute in the vapor pressure, right? Because it is non-volatile. So total pressure of the solution, it is coming out only because of water, because water is volatile. That's why I am taking only water. Let's put the value. They gave the P0 as 23.8 mm of Hg into how much? 0.9827. 9827. It will come up to be 23.40, something like that. Okay, mm of Hg. Okay, so your answer is going to be A. I guess it's clear to you. Let's proceed further. Okay, so this is elevation in boiling point. So basically what happens, vapor pressure is decreased, right? So as a result of this boiling point, the solution starts to boil in a higher temperature than that of the pure solvent. That is the elevation in boiling point. Initially it was boiled here, now it is getting boiled here. The boiling point increases. Okay, so here comes the formula. You can see delta TB equals to Kb into M. Okay, Kb is the constant, that is called ebullioscopic constant. Okay, now M is the molality out there. So molality you can break down with respect to W2 by M2 into M1 into 1000. So utilizing this formula we can target one numerical. Very important numerical. Okay, elevation in boiling point was 0.52 degrees Celsius when 6 gram of a compound X was dissolved in 100 gram of water. The molecular weight of X. Okay, fine. Let's do it. Simply I am going to put the formula like this, Kb into M. So from here I can write it, delta Tb equals to Kb into molality. Let's break down, W2 by M2 into W1. I will put it in gram into 1000. That is a formula. Once you wrote the formula, na, half of the problem is sorted. Now let's put the value 0.5 2 Kelvin kg mole inverse into W2. W2 is 6 gram. 6 gram, okay, into 1000 divided by 0.52 this, okay, into okay. Next we will proceed with W1. W1 is here 100 gram. Yes, everything I wrote correctly. Let me just check once. Yes, 100 gram of water. Okay, fine. So now let's proceed. If you just calculate this entire thing, it will come up to be 60 gram. 60 gram per mole. Okay, so your answer is going to be, okay, M2 you have to find out. M2 you have to find out. I guess it's clear. That's going to be 60. Okay, I guess it's clear to you. Let's proceed further. Okay, this is depression in freezing point. So again, same thing I am going to tell, that whenever that non-volatile solute is added, the vapor pressure of the solution, it decreases. Okay, so freezing point becomes lower than that of the pure solvent. Initially it was freezed here, now it is freezed here. Okay, so I guess it's clear. Same thing, same terminologies here, but only the the constant, that is Kf, okay, cryoscopic constant, okay, and molality, that's baked out. Okay, let's proceed with one of the problem. So same thing we can do here as well. The molality of a solution containing a certain solute, if there is a freezing point depression 0.184 degrees Celsius. Okay, so yeah, it's going to be even easier. Delta Tf is basically m into Kf. From here I can just simply calculate m. M only they asked, right? So m is basically delta Tf divided by Kf. Let's put the value 0.184. 0.184 divided by 18.4. From here I will get 0.01. So A is the correct answer. I guess it's clear to you. Let's proceed further. Osmotic pressure. Okay, so osmotic pressure is what is osmosis? At first understand, osmosis is basically two different solutions, they are separated. Okay, one is of higher concentration, one is of lower concentration. They are separated by using a semi-permeable membrane. Okay, what is semi-permeable membrane? It allows only the solvent. Okay, so what happens? Basically the solvent from the low concentration zone, it goes towards the high concentration zone in order to make it isotonic, make it equal concentration, okay, through semi-permeable membrane. This is called osmosis, right? So if you give a pressure that stops this solvent flow in osmosis, that is called osmotic pressure. Okay, so the pressure that can stops the flow of solvent is called osmotic pressure. Okay, I guess it's clear to you. This is a formula, that is pi is the osmotic pressure, pi equals to CRT. What is C? C is a concentration. So let me just tell you, C is basically N by V, right? So N can be written as W2 by M2, okay, into V. Okay, that's what is written here. Okay, N is replaced with W2 by M2 into volume of the solution. Okay, so once it is in the ml, so here you have to multiply with 1000. That's what they have given here. Okay, into RT as usual. I guess it's clear to you. Let's proceed. Yes. So here, what is isotonic solution? Isotonic solution means whenever two solutions, they are having same osmotic pressure at a given temperature. Okay, what is reverse osmosis now? Okay, so now just let me just give you the example of it. Sorry. So let's say here I am having SPM. SPM means semi-permeable membrane. Here I am having seawater. Okay, and here I am having normal water. Okay, so now here it is concentrated because in the sea water we know there are so many salts and all. In the normal water it is diluted. So in usual method, what it should happen? The solvent should go from here to here, low concentration to high concentration, right? But whenever pressure is greater than that of the osmotic pressure is given that side, okay, some extra pressure is greater than that of the osmotic pressure, what will happen? It will force the solvent from the higher concentration zone to lower concentration zone, the reverse of the original osmosis. Okay, usually in normal cases what happens, from the low concentration to high concentration zone the solvent moves, but whenever the pressure is greater than that of the osmotic pressure, then it will force the solvent to travel from the high concentration zone to low concentration zone. That is reverse osmosis. Okay, so utilizing this, what we do? Desalination of seawater. I guess it's clear. This is a very important, okay, this reverse osmosis, what do you mean by reverse osmosis and one application of it, okay, it's very important for the board purpose. Okay, one question, isotonic solution have same osmotic pressure. Easy question. Let's proceed. One more, it's a PYQ. Which of the following colligative properties can provide molar mass of the protein, polymers and the colloids with a greater precision? So that's gonna be osmotic pressure, my dear. So basically this is a question very important. Sometimes they ask this type of question as well, why osmotic pressure? So basically depression in freezing point, elevation in boiling point, or this type of colligative properties, they are temperature dependent, right? You have to vary the temperature, right? So, and here whenever you are dealing with the very big biomolecules, right, they are very much temperature sensible, okay, they can break down in high temperature or low temperature. So sustainability, in order to maintain the sustainability of those particular proteins or colloids or any kind of polymers, we should avoid like varying the temperature in that extent, whereas osmosis can be done in normal room temperature, right? So that method is more accurate. And in other cases you can see we have to use the molality, but in osmotic pressure number of moles will work and the calculation part is also very much convenient, right? So we can use the osmosis. Next, abnormal molar mass. Okay, so this is basically why this happens. This is because of the association or dissociation of the solutes. Why it happens, let me tell you. Once you are having NaCl in your hand, it's NaCl, single particle, but whenever you are just putting it into the solvent, then what is happening? It's breaking down into Na plus Cl minus, dissociation takes place, right? So this particular thing can affect the the solution as well. I mean, this type of association and dissociation also may affect the colligative property as well. Okay, now let me just give another example. Let's say you are having acetic acid, you are putting it into the water. What happened? Acetic acid will dimerize. 2 units of acetic acid, they will merge with respect to hydrogen bonding, right? Dissociation takes place, right? So this is abnormal molar mass, right? So this can be corrected using the Vant Hoff factor. So here comes the I is the Vant Hoff factor. Here comes the formula that can be used in general. Just you can make a note of it. And next, for association, this is in terms of alpha. Alpha means degree of dissociation, right? So for dissociation case, it can be I minus 1, N minus divided by N minus 1. What is N? N is the, effective molar mass. Let's say I am having NaCl. So NaCl will break down into Na plus Cl minus. So after dissociation, it will be 2 particle, right? So N will be 2, like that. If you are just taking association, so what will happen here? Association means whatever, let's say I was having acetic acid, 2 acetic acid will merge and it will give you 1 dimer of acetic acid. So N will be 2 here, sorry, 1 by 2 here. N will be 1 by 2 here. So this type of thing. I guess it's clear. Let's proceed with a numerical problem. Okay, I guess it will be clear to you now. So here the Vant Hoff factor for 0.1 molar barium nitrate solution is 2.74. So degree of dissociation you have to find out. Okay, it's an easy one. Directly we can apply the formula. So barium nitrate, let me just find out the value of N at first. NO3 whole twice. So they will definitely dissociate to give you Ba2 plus 2NO3 minus. So how many particles? I am getting 2 plus 1, 3 particles. So N is going to be 3. Now let's apply. Alpha is basically equals to, for the dissociation formula, I minus 1 divided by N minus 1. I minus 1 divided by N minus 1. So if you just put the value here, what I have to find? I have to find alpha. Okay, fine. So I is basically this. Okay. So wait, let me just write it down in this way. I is basically equals to 1 plus N minus 1 into alpha. Same thing, just multiplied. Okay. So I value is given as 2.74. 2.74 equals to 1 plus 2 alpha, right? Okay, because 3 minus 1, right? 3 minus 1 will come to 2 alpha. So alpha will come something like 2.74 minus 1 divided by 2. If you calculate, it will come as 0.87. Alpha will come as 0.87. So percentage alpha will be 87%. Option B is the correct one. Okay, I guess it's clear to you. Okay, so just let me tell you something here for the, if you are having those type of solute, like, let me just give you an example. So let's just take, I'm having the aluminium sulfate, Al2SO4 whole thrice. Okay, for this, if you dissociate, it will come as 2Al3 plus 3SO4 2 minus. For this case, how many ions I'm having? I'm having total 5 ions. So I will be 5 for this case. Okay, let's say you're having example of aluminium chloride. Okay, so here also Al3 plus 3Cl minus. Okay, so total how many ions you are getting? You are getting total 4 ions, so I will be equals to 4. Now if I am just asking, let's say delta TB will be, in which case I am having, let's say, same molality, 0.1 molar I have taken for both of them, same molality. Okay, now which case delta TB will be more? Okay, so basically the formula I can apply, I into Kb of M. M is equal for both the cases, right? But for this case, it will be delta TB equals to 5 into Kb into M, and for this case, it will be delta TB equals to 4 into Kb into M. So definitely this is going to have maximum elevation in boiling point. Okay, this type of question also may come. So definitely don't worry, we will trigger the question as well in the live session. I will come up with the live session with more number of questions so that this chapter, all the concept you get proper idea and the concept becomes crystal clear. Okay, so let's go back. Yes, here I guess it's clear now. Let's proceed. Yes, we are done here. So I guess the entire thing I covered and you people also understood and you made a proper note out of it. We will definitely come up with the previous year question of the KCET, and a little bit I will try to trigger the MCQs of the board level as well. I will mention that in the live session itself, and you people also please be prepared with your doubts as well. So don't forget to like, share and subscribe our channel, and stay tuned to get more informative videos. Thank you so much.